We're going to start off today talking about sets. So sets are basically like the building blocks of mathematical objects. They're kind of like math's version of atoms. So a set is a collection of objects, and objects that are in a set, we call them elements. So you are an element in the set of students taking Math 220 this semester. I am an element in the set of faculty at St. Martin's. We can really think about just about anything in life as an element of a set or a set itself. So really, if you start kind of practicing that a little bit, then you'll get into this vocabulary thing really fast. So in math, when we're writing sets, we use capital letters generally. So whenever you see a capital letter in this class, chances are really good it's talking about a set. And when you see a lowercase letter, chances are pretty good that it is talking about an element of a set. One of the things that we like to do a lot of times is we like to have the lowercase letter be an element in the set that is the capital letter. So I might have a lowercase a is an element in the capital A set. And sometimes we even go so far as to put subscripts on those lowercase letters. So I might have a sub 1, a sub 2, and a sub 3 all being distinct elements in the set A. And that way I get to use only A's to represent all of those elements in that set A. So a little bit of notation that comes out other than these capital and lowercase letters is this like rounded off E looking thing. So we can see that when we're talking about this like A being in A, when an element's in a set, we use this rounded off E thing to say it's in it. So if I want to say the element A, lowercase a, is in the set A, I use the rounded off E thing opening up towards the capital A that it's in. And I've then said A is in A. So that rounded off E thing, whenever you see it, you should be thinking is in, all right? And then, like most math symbols, we can say it's not in. We can add that word not just by putting a slash through it. So same way that you make something not equal by putting a slash through that equal sign, you can put a slash through that rounded off E, and we have A is not in A there. Notice when I'm saying this, I'm not distinguishing between lowercase and capital A, because when we talk about A being in A, the element is always the thing that is in the set, so it goes without saying. And you can get to the point where you're not saying capital and lowercase, and it should make sense to the person listening. All right, so when we talk about describing a set, we describe a set by talking about what's in the set, all right? So things that make sets unique are the elements that are in them. So whenever we do that, we use curly braces to talk about what's in a set, and we put commas between the elements in the set. So here I have a set S that contains the elements of the numbers 1, 2, and 3. If I didn't have the commas there, I wouldn't know if it contained the separate numbers 1, 2, and 3, or numbers like 12 and 123, all right? So the commas are important there. Please make sure you're using those, okay? The set X there, it contains the numbers 1, 3, 5, and then you'll notice that we've got like some dots there, right? And then it goes up to 49. So sometimes you can do some pattern matching here. And so this set X with all those dots are representing all of the positive odd integers, right? Going between 5 and 49. We're not writing out all of those, but we can notice 1, 3, 5 are all odd, they're all positive, they're going in ascending order, and then 49 is our hard cutoff. All right, so we could describe that set as the set of all positive odd integers less than 50. All right, my set Y there, similarly, you can do some pattern matching. 2, 4, 6. We notice that we're doing even integers here. All right, so we count up by even numbers, and there is no hard end. So this is really just all the positive even integers, right? Start at 2, just keep on going, every even integer. And finally, we have this special set called the empty set, and it's a set that has nothing in it. So we do that, the 0 with a slash through it, all right? that's telling us that there's nothing in it, and that is the notation for it. All right, so a couple of examples just to get you thinking a little bit. Sets can contain sets as elements, all right? This is weird. So here I have a set S that has an element of the number 1, an element of the number 2, and an element that is the set that contains the numbers 1 and 2. And then it also has a set in it that is the empty set. So there's actually 4 elements in my set S. 2 of them are sets, all right? And sometimes, to make things a little simpler, instead of having curly braces nested within each other a whole lot, we'll define the sets that are within a set with other letters, and then include the letter instead of the second set of curly braces in it. So if I define the set that contains 1 and 2 as set C, then I can include C in S instead of those curly braces with the 1 and 2. All right, and similarly here, T, I have a set that contains the number 0, the set that contains the numbers 1, 2, and 3, and the numbers 4 and 5. So T itself does not contain the number 2. 2 is not an element of T. Neither is 1, neither is 3. They're within the set that is contained in T. All right, it's just some nuancy stuff. All right. So there's one other way that we write out sets, because sometimes listing out all the elements is not something that we can really do, even with the pattern matching, putting some dots. So one way that we deal with that is we can use this notation where it's called set builder notation, where we list out, hey, S is a set, and then we put the variables, which are representing the elements. So right here, I've got X, all right? So S is going to contain all the elements X. The colon we read as such that. So S is going to contain all the elements X such that P of X. And P of X must be true. Notice here they look identical, except I've got a colon versus a vertical bar. So colon, vertical bar, they're interchangeable. We'll say such that for each of them. And if you say the word such that every time, it's going to make sense, all right? So here I've got the set S is the set of all elements X such that X minus 1 times X plus 2 times X plus 3 equals 0. So to figure out what's in S, I would solve this equation right here, and I would find out that the elements that satisfy that equation are 1, -2, and -3. So the elements in S are 1, -2, and -3. So it's just a different way of writing that. Similarly, T there is a set of all elements X such that the absolute value of X equals 2. Same idea, all right? So I think about what elements have an absolute value of 2. I have -2 and 2. That's the only elements in T there. All right. So here's an example where we get to build that up a little bit. So if I have A being the numbers basically 3 through 20, right? That's my set there. So B is going to be a set where I've got X is in A, and X must be, so elements X that are in A such that X is less than 8, all right? So that's what my set B is going to be. So I think about that. The things that are in A, I have numbers starting at 3, right? Integers starting at 3. So I have 3, 4, 5, but I have to stop at 8, right? Because X has to be less than 8. So I'm actually going to stop before I get to 8. So I have 3, 4, 5, 6, and 7. Those are my elements in B. All right, so there's some special sets of numbers that we're going to talk about in this class, and we're going to use these a lot, so please take some time to get comfortable with them. Possibly the most important is the rational numbers. So rational numbers can be expressed in the form of a fraction. That definition will be a close friend of yours. Please, please remember it. All right, so rational numbers can be expressed in the form m over n, where m and n are integers, all right? And the denominator is not 0 because we can't divide by 0, right? So this is basically the set of all of the things that we can write as fractions. Whole numbers can be written as fractions because we can write them over 1. All right, denominator of 1. So if that's what rational means, irrational, guessed it, it means not rational. All right, so a number that is not rational is irrational. All right, and then we have a set of numbers that are a little bit more complex, no pun intended. All right, so the complex numbers, these are the numbers where you have a square root of -1 taking place in them somewhere. So in classes previous, you've probably written no real solutions. And here we're actually going to dive into these numbers a little bit. So if you haven't heard of I, it's okay. As we get to this stuff, we'll spend a little bit more time with this. All right. So whenever we're talking about the sets of different types of numbers, here we're going to use these blackboard letters. They're basically the ones that have the double bars in different places. So we have natural numbers, which are the positive integers. Those are the counting numbers. So 1, 2, 3, 4. Integers are all of those numbers also with the ones that have negatives, right? So we've got all of our negatives, 0, and then all of our counting numbers. We just talked about rational, irrational, and complex numbers. Real numbers are all of the rational and the irrational numbers. So all the numbers that we can write as decimals. All right. So the final thing when we're describing a set, we talk about how big the set is. All right. So a set is defined by how big it is. All right. So if a set has 2 elements in it, then we say it's cardinality, and we use those absolute value bars to find the cardinality to say that that's what we want. It has 2. So my set there, A, has 2 elements in it, the numbers 1 and 2, and so its cardinality is 2. My set B there has 4 elements. Remember, this is our example where we've got sets as elements, right? And so the cardinality of my set B is 4, right? And then, just a really quick thing, the empty set has nothing in it. So the cardinality of the empty set, 0. All right. And when we're talking about a set, we say it's finite if we can actually tell you what the cardinality is. If the cardinality is infinite, then it's an infinite set. All right. So if I ask you what the cardinality is and you say, I could just keep going forever, I can't actually count it, then that's not, it's an infinite set, right? A finite one is where you actually could, in theory at least, count all of the elements in the set. So there's some examples here where you get to try and figure out what the sets are. I'm going to skip this over. These slides are available to you though, but you can go through this and give these a try, all right? And another example problem that, again, solutions right there. And we're going to skip over it in this, but again, the slides are posted, so take some time to go back and make sure that you understand it. All right, the second topic for today. It's a much faster one, I promise. Subsets. All right, so a set is a subset if all of its elements fall in another set. All right, so if A is a subset of B, if every element of A is also in B. All right, so if I think about the math faculty here at St. Martin's, right, that is a subset of the full faculty at St. Martin's. Every math faculty member here is also a member of the full faculty. All right, that's the idea. Okay, so we can do this, that our natural numbers are a subset of our integers, the rational numbers are a subset of the real numbers are a subset of the complex numbers. They're all the ones that have 0 times I. All right, and we can do it with other sets as well. Please note, the empty set is a subset of every single set. All right, so again, here's an example that I am going to leave for you to look at in the slides on your own, right? We are going to take a look at this one though. So example 7 here. We've got S. It's a set that contains 1, the set that contains 2, and the set that contains 1 and 2. So we want to know which ones of the following are elements of S. Well, the set that contains 1 is not an element, neither is the number 2, and neither is the set that contains the set that is 1 and 2. So we only have the element of the number 1, the element of the set that contains 2, and the element of the set that contains 1 and 2. All right? And then when we're looking at the subsets, basically we're taking those elements, so those 3 elements, and we're grouping them up in every possible way. So the set that contains 1, well, that is a subset because I have the element 1 here. The set that contains 2, that is not a subset because this is the set that contains 2 as an element. So I would have to have the set that contains the set that contains 2 in order for it to be. All right. So similar deal here, the 1 and 2 thing, I don't have that. But I do have a set that contains a 1 and the set that contains 2. That's taking my first 2 and putting some braces around them, right? And then again, I have the set that contains the set that contains 1 and 2. So I'm taking this third element here and putting braces around it. So whenever you're building up a subset, you basically need to be able to put braces around some subset of the elements that are in there. And if that's not a thing that's happening, then it's not a subset. All right, so a couple of things. When we're talking about all of the possible elements of all of the possible world, we talk about the universal set. It's everything, all right? And we can talk about like what universe we're functioning into. So you can function like within like the students at St. Martin's within the universe of people. And in some way, like you're dealing with a subset in that way, all right? So the universal set though, you can specify what that set is, how big you want to get, okay? Otherwise, we have a couple of things. So we have things called open intervals. So we can talk about all the real numbers between 2 numbers. That's what an open interval is. We use parentheses, so rounded, to function this, or to notate this. So we've got these rounded parentheses, and it's all the real numbers between 2 numbers. All right, so if I'm looking between 2 and 5, then it's everything between 2 and 5, not including 2 and 5. You don't get to include the ends. So there's some examples of some numbers that are in that set and some that are not there for you. All right, if we're going to have open intervals, we've got to have closed intervals also. All right, so closed intervals, we use square brackets, all right, hard corners, and that's saying that we're going to include the ends. So if I'm going between 2 and 5, I'm actually going to include the numbers 2 and 5. That's the only difference between an open and closed. All right. We can have half open and half closed, so you can choose to include the upper bound or the lower bound without including both or without excluding both. That's an option. And notice that every time we ever use infinity anywhere, we use open, because infinity is not a number. So saying you're going to include infinity is just not, it's nonsensical. So we always use parentheses around infinity because we can't actually loop it in, right? 2 sets, they're equal if they have exactly the same elements. There's no other way. Like the cardinalities being the same is not enough. They have to have the same exact elements. And it can't be that one of them contains 2 and one of them contains the set that contains 2. They have to have the same exact elements. One of the ways that you can really get a feel for sets and especially subsets, I highly encourage this, is draw some Venn diagrams. All right, so draw a Venn diagram and say and put elements where they belong, okay? So here I've got two sets. I have A and B. When I look at this figure right here, this is telling me A and B have nothing in common, right? They're just living there. If I have them overlapping like this, in the way you're used to seeing a Venn diagram, I have my set A, and I have X is in the set A, but it's not in B. I have Y over here is in B, but not in A. Z is living in the middle. It's in A and B. It falls in both circles. And I have W up here that doesn't live in either A or B, all right? So when we talk about a proper subset, we're saying that they're not equal to each other. So A is a subset of B, but A is not equal to B. So there's some element in B that is not in A. So here I've got S is a subset, a proper subset of T, because T has the numbers 3 and 6 in it, and S does not. And then we've got this idea of a power set. You can build up a power set of a set by making a list of all the possible subsets of that set. So here's an example. All right, so here I've got A is equal to the empty set. So the power set of A is the set that contains the empty set. That's the only thing that's in it. So we've got that. If I take a look at the set that contains A and B as elements, then the power set's going to be the empty set, because that's a subset of A. The set that contains A is a subset of A. The set that contains B is a subset of A. And then the entire set A is a subset of itself. All right, so the power set is always going to contain the empty set, and it's always going to contain the full set itself. If those things aren't the same, then you're guaranteed your power set has at least 2 elements in it. And then it also contains all of the subsets in between that. So we see how this builds up really fast. The cardinality of the power set of the empty set is 1. If there's 2 elements in there, I have a cardinality of my power set being 4. If there's 3 elements, you guessed it, power set cardinality is 8. All right, and you've got all of the subsets there listed. So the power sets actually have 2 to the n elements in them. They build up really fast. And this example I'm going to leave you to take a look at. All right, remember the number of braces, it matters. Sets in sets, yeah, all right? But that is all there is to sets and subsets. And I know it was a whirlwind. I know it's a lot of vocabulary. We'll keep on using it so that you can get comfortable with it.